right, so day 24, our review day. Couple of reminders about the tests first. So test is tomorrow. Since I will not be here, you are allowed to use your notes on it. You will only have the amount of time of the class period to upload it though, so make sure you do the test during the class period and upload it during that time. You should not be communicating with anyone during the test. So we're going to go through the homework, and then we're going to do like 3 problems that in years past students have asked to go over on our review day. So first one, we want integral of sine x squared as an infinite series. So start with our sine x, which we know. So you got your odd powers, odd factorials, alternating signs, and then you have it there on the right as a infinite series in general terms. So then we want to sub in x squared. So over in the infinite series, if you sub in x squared, your exponent is now 4n plus 2. Well, then we want to take the integral. So when you do the antiderivative, note you have the c, and then over in our infinite series, your exponent went up 1, so now you have 4n plus 3, and divide out front by 4n plus 3. Well, it's a definite integral, so we're going from 0 to 2, so the c doesn't really matter when we do the definite integral. When you put in the 2, you'll get the summation that you have in the green, but with 2 filled in for x, minus, when you sub the 0 in for x, it's going to wipe everything out. So it just has the 2 filled in. So then we wanted to estimate our error in our approximation. Oh, wait, there's a part before that. Sorry, we want to do the partial sum for the first 3 terms. So take your first 3 terms and fill in. So that's the 1/3 x cubed minus 1/7 x to the 7th over 3 factorial plus 1/11 times x to the 11th over 5 factorial. Fill in your 2, and we get that value either in fraction form or to 3 decimal places. It's an alternating series, so we can use alternating series error bound. Our max error is the absolute value of that next term. So the next term would be a negative 1/15. We'd be raised to the 15th, and we'd be over a 7 factorial. So fill in 2, take the absolute value, and we would either have that fraction or out to 3 decimal places form. Maclaurin, so we know it's centered at 0, so we can think of our nice one. So start with our e to the x, where we have all positives, we have all the powers, all the factorials matching on the bottom. Over on the right, we have then the general series. Well, then we want to just multiply by x. When you multiply by x, x times x to the n is just x to the n plus 1. And we get our series that's in the box there. So in general, we have our derivatives at that center times x minus our center raised to the n over n factorial. So here's our derivatives. We have x minus 2 our center to the n over n factorial. Notice the n factorials wipe out, so that's why in the box version of that series is the simplified form. So now we want to do the interval of convergence. So we got to do limit as n approaches infinity, absolute value of the next term divided by the current term. So fill in your n plus 1s. A whole bunch of x minus 2's wipe out, except for 1 on the top. Stick your n's over each other, so when n goes to infinity, same degree, so leading coefficient ratio is just 1. Now we just have x minus 2 times 1. We need that to stay less than 1 in order for it to converge. So set up your negative 1 less than x minus 2 less than 1, add the 2 over. So initially we've got from 1 to 3, but then we got to test our endpoints. We're subbing our endpoints into here. When you sub in 1, you'll have negative 1 to the n over n plus 1. That'll be an alternating series. Each term is smaller than the previous, and as n goes to infinity, our terms are approaching 0. So therefore, we can say it converges by the alternating series test. When we sub in 3, we get positive 1 over n plus 1. So we're going to compare it to our harmonic. Our harmonic we know diverges. So if we do limit as n approaches infinity of them divided, we'll end up getting 1, which is a positive finite value, greater than 0. So therefore, we can say the one we were looking at, the 1 over n plus 1, diverges by limit comparison test. So our final interval of convergence includes the 1, but does not include the 3. So our front mess out here should include our nth derivative over whatever our factorial is. So this is saying we want to find the fifth derivative at 3, at our center of 3. So what we do is we fill in 5 for n in that part that I just bracketed, and that's what's on the right of our equation there. We know that should equal the fifth derivative over 5 factorial. So neaten up the right, do your 5 factorial, multiply the 120 over, and then we know that our fifth derivative should be that fraction that is left. So we're going to start out with cos x, our basic form for that. For this one here, you didn't necessarily need the general over on the right. We'll be able to figure out without it if you just write out a couple terms. Sub in the x squared, subtract the 1, and then divide everything by x to the 4th. So we've got this here that we can work with. So now do limit as x approaches infinity. All the terms wipe out except for that negative 1 over 2 factorial. So we get negative 1/2. And here's just an example of doing that same limit, but with L'Hopital's. So you get 0 over 0. You would do the derivative of chain rule on top. You get the x's and the 2's could wipe out to simplify it, but then you still have another 0 over 0. So you got to do L'Hopital's again. You can divide a 4x out of them, and then you would be able to do direct substitution to get negative 1/2. So the L'Hopital's answer would not be correct for this problem because it said we had to use series, but they could easily give us this limit on a question and not say, like on the AP I'm talking, not on our unit test, but on the AP exam they could give this limit and you would have to do it, but could also do it by L'Hopital's. Okay, so the L'Hopital's would be the different method that they were talking about there. So we want to express this as a Taylor series, so our final answer should be some general summation. So start with our basic e to the x, and you've got your general summation over on the right there. We'll now subtract the 1. Well, when you subtract the 1, we're basically starting now, instead of at 0, we're starting here in our series, so just change your bottom number to n equals 1. Divide by x, so now x's power is to the n minus 1. We're doing integrals, so we're going to take an antiderivative. It's an indefinite integral, so you need to have your c plus out front. The exponent goes up to n and divide out front by n, and we get then the series that is in the box. All right, so these can sometimes be challenging. First thing to probably notice is that we could start with 1 over 1 minus x, which is just our geometric where we're starting with 1 and multiplying by x each time. But we're going to need alternating signs. So imagine we sub in negative x. So now we're with 1 over 1 plus x, and we've got the alternating signs now. Well, what we have is the antiderivative of that. So if you take the antiderivative of 1 over 1 plus x, that's really natural log. And then that matches with what we have. In B, notice we've got odd factorials, odd powers, and alternating signs, so we want to think sine. So start with your basic sine, and then we can get what we have by just subbing 2x in for all the x's. So sine 2x would be our final answer there. In C, we want to recognize we're starting with 8x squared and we're multiplying by negative 1/2 x squared each time. So if we take our geometric infinite sum setup, put the 8x squared on top, 1 minus a negative 1/2 x squared on bottom. And the last one of this one, 4, notice we've got all the powers and all the factorials, so we should be thinking most likely in E. Notice we got something missing, and the signs are alternating though. So start with your e to the x, sub in a negative x to get the signs to be alternating. Once they are alternating though, they don't match our alternating. So for example, we want the x squared to be negative, but we have x squared to be positive now. So negate everything, and that'll get what we want, but then we don't have that constant negative 1 on the front, so we need a plus 1. In A, we've got odd powers, but we've got even factorials. We're alternating signs. So because even factorials, alternating signs, you probably want to think cos to start out. But the problem is cos should be 1 and then minus x squared over 2 factorial plus x to the fourth over 4 factorial. So all our powers of x are 3 too big, so we'll multiply everything by x cubed. In B, we've got all the odd factorials and alternating signs, so we want to think sine to start out. But all of our powers, all those odd powers, are doubled. So we want to fill in x squared where x is, so we end up with sine x squared. The signs in C should pique your interest because it's not alternating signs. Notice you have plus plus, then minus minus, then plus plus. It's got all the factorials, all the exponents. So what this is, it's just a combination of sine and cos. Sine and cos were just added together to get that combination. In 9, we're starting with 3 and multiplying by half. So 3 over 1 minus our r gives us 6. We've got odd bases, so we want to think eventually that we're going to have arctan there. Arctan is x minus x cubed over 3 plus x to the fifth over 5 and so on. And we just had 1's filled in for all of them, and arctan of 1 is just pi over 4. In C, you want to recognize we have all the factorials. They're all positives, so that looks a lot like e to the x. Well, jump to like the third term, we have 9 where x squared should be, so that's a 3 filled in. We have 27 where x cubed is, that's a 3, so we have e to the third. And then for D, we have our natural log of 1 minus x, which would initially we would think of it as negative x minus x squared over 2 minus x squared over 3 and so on. Well, notice the 2, 4, 8, 16 can be thought of as 2 to the first, 2 to the second, 2 to the third, 2 to the fourth. So really we have 1/2 that was subbed in for x. So then the 1 minus the 1/2 gives us natural log of a half. In 10a, we've got odd factorials, odd powers, alternating signs. We want to think sine. So if you think of your sine x of x minus x cubed over 3 factorial, and so on, we just have negative 5 filled in for all of them. So the boxed one is probably the logical thing that you would have, but based on our trig properties, minus sine of 5 is technically the same thing as well. In B, we want to recognize that that's just our factorials in the bottom, 2 factorial, 3 factorial, 4 factorial, and so on. So that would lead us to think e, but notice our powers are, or our signs are changing. So we would want to think e to the negative x. So from that e to the negative x, if we subbed in 1 right now, a lot of the stuff would match up, but we would have a 0 on the front. Because if you put in 1 for all these here, all of this stuff would match, but we'd have a 0 on the front. So you would need a +1 along with the 1 filled in for x in order for it to match up. In C, we're multiplying by -1/6 each time. We started with 216, so 216 over 1 minus a -1/6, you end up with 1296 over 7 when you neaten it up. And for D, we got all the factorials. They're all positives. So we want to think E, and E has natural log of 4 subbed in. So that's really just 4. All right, so we're going to look at 3 different ones that in past students have asked for. So we're going to look at number 5 first. So we want to use a third degree Maclaurin polynomial to approximate the value of e to the 0.02. So we'll start with 5a. So we know that e to the x is all of our factorials, all our exponents, and the positives. So it's 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus ... We don't need more than that because we want the third degree. So now we want to approximate e to the 0.2. And we'll do that by just using those first 4 terms, which would be the third degree. So you're just putting in 0.2 for each of them. And when we sub that in, that tells us that e to the 0.2 is approximately 1.22. And they tell us we're at around to 4 decimal places, 1.2213. So then we wanted to determine the upper bound for our error in our approximation. So our 2 errors we have Lagrange and we have alternating series error bound. This was not alternating, so we have to use Lagrange. So we're on the interval from 0 to 0.2 because our center with a Maclaurin was at 0 and we were subbing in 0.2. So to start out for our Lagrange error, we're going to have that m value. Then we're going to have absolute value of 0.2 minus 0 to the next degree, so 4 over 4 factorial. So m needs to be the upper bound on our interval. Well, if you think of e to the x is an increasing function. So on that interval, we want to think e to the 0.2 is our upper bound. So let's pick something nice that we know is greater than that. 0.2 is really 1/5. 1/5 is really 5th root. So this is really the 5th root of 2.7. So let's pick a nice 5th root that we know. Let's do 5th root of 32. That's our smallest nice one because you don't want to do 5th root of 1 because that's smaller than it. 5th root of 32 we know is 2. So we can put 2 in here for m and be confident that the e to the 0.2, which is 5th root of about 2.7, is definitely going to be smaller than that. Because remember, you want to pick something nice for your Lagrange. So when we punch this in, we get 0.000133. And it doesn't say where to round to for this, I don't believe. It doesn't. And I would say keep it out to 3 significant figures. because our normal AP rounding standard would say that this is 0 for the error, but this is definitely not an error of 0. Next one we're going to look at is 7. So we want to find the interval of convergence of that power series. So interval of convergence, we'd start out with our ratio test. So we're going to do the limit as n approaches infinity. Absolute value, we'll do our next term divided by our current term. So the next term will be x plus 4 to the n plus 1. And again, this is number 7 we're doing. Over n plus 1 times 2 to the n plus 1. We're going to divide, so we'll do a keep change flip. So we'll end up with times, for our current term, 2 to the n times 2 to the n over x plus 4 to the n. Absolute value equals, this will be limit as n approaches infinity. So we've got a whole bunch of x plus 4s. All of them except for 1 is going to wipe out. We have a whole bunch of 2's. All but 1 on the bottom is going to wipe out. And then we'll be left with an n over an n plus 1. Well, as n goes to infinity, that second fraction, because it's the same degree, will approach the leading coefficients ratio, which is 1 divided by 1. So this is just equal to the absolute value of x plus 4 over 2 times 1, which we want that to stay less than 1. So let's set it up without the absolute value. We'll have negative 1 is less than x plus 4 over 2 is less than 1. If we multiply the 2's, we'll get negative 2 less than x plus 4 less than 2. And subtract the 4's over, we'll get negative 6 less than x less than negative 2. So that's our initial interval of convergence. But we always then have to check the endpoints. So we are checking them. In our original here, we're filling in our values of x. When we sub in negative 6 for x, we're going to get negative 2 to the n in the parenthesis there. So we'll have sum n equals 1 to infinity. We'll have negative 2 to the n over n times 2 to the n. Well, those ones that are written to the n, think of them as being like negative 2 over 2 all to the n. So this is really sum equals n equals 1 to infinity of negative 1 to the n over n. So this is going to be alternating. Each successive term is less than the previous one. And our limit as n approaches infinity of our terms will go to 0. So we can say, therefore, this converges by the alternating series test. For our other endpoint that we'll check x equals negative 2. Again, that's getting subbed in here. Negative 2 plus 4 will give us a positive 2 to the n. Well, now the 2 to the n's just divide out. So we'll have 1 over n, which diverges since it is the harmonic. Could also say diverges since it's a p series where p is greater than 0 or less than or equal to 1. So therefore, our interval of convergence will include the negative 6, but not include the negative 2. Real good chance you'll see one of those on your test tomorrow. Real good chance you'll see one of those on the AP exam. Really popular question. And then We're going to look at question 33. 33 is a common way that Lagrange error is represented on the AP exam. With Lagrange error, that m value, that nice upper bound of your nth derivative, on the AP they like to make sure everyone's picking the same value there, because otherwise it's a little bit subjective of what's bigger but nice. So here they tell us a value at x equals 3. We know the first derivative at x equals 3, the second derivative at x equals 3, and then they tell us that that next derivative, we're guaranteed that it is less than or equal to 8. Now I should have specified when we did that other one with Lagrange, so I think that was number 5. The reason we were considering e to the x here and that e to the 0.2 was less than something is because that, let's see, we had third degree. So that fourth derivative of e to the x is still just e to the x. So when it's e to the x, it's kind of coincidence that we're just still looking at e to the x, because really we're looking at the fourth derivative function. It just happened to be e to the x still in this one. So going back to 33, first off, we want to approximate f of 3.1. Well, the best we can do for that is to do our second degree Taylor polynomial, because we only know up to the second derivative. So it's approximately our value at 3 plus the value, oops, actually it's going to be minus because we have minus 3. So minus 3, and this is technically over 1 factorial. And then we have x minus our center to the first. Then we've got our second derivative over 2 factorial times x minus 3 to the second. So we want to then find f of 3.1. So I'll neaten this up a little bit as I'm doing it, but we're just filling in 3.1 for each of these. And when we do that in our calculator to 3 decimal places, we get 1.705. Well, we want to know how close is that? And this is where the fact that our third derivative is less than or equal to 8 comes into play. We're going to do our Lagrange error bound. We know that our error is less than or equal to the maximum value, the upper bound of our next derivative, and then the absolute value will have the value we're checking at minus our center raised to our next power over our next factorial. Well, that upper bound for the next derivative, they told us the third derivative is less than or equal to 8. So we'll just put 8 here, and this type of question then ensures that everyone is using the same value there. So if we put this in the calculator, we would get 0.00133, and then that would be repeating after that. So that's a really common way that Lagrange error shows up on the AP exam, again, because it forces everyone to use the same thing for that value of m. A reminder that the worked out solutions for all of these questions is on Schoology. If you go to the class materials folder, Unit 7, it'll say Unit 7, Exam 2, Worked Out Solutions. So you can be checking those to check your work as you're working through this. Have a great rest of your day.